A rational function is defined to be a division of two different polynomial functions. Basically, this chapter we're going to be focusing on all the properties of such functions and discussing things like asymptotes and behavior towards the asymptotes, and really getting at all the different algebraic traits like intercepts. And I'm going to teach you how you can find all of those different properties. We refer to the properties of these things as all of the special aspects of those functions, and rational functions have a lot due to the complexity. And if you were to take, also just to sort of say, when you take one polynomial and divide it by another polynomial, it creates this new type of function. Like we kind of talked about, if you add, subtract, or multiply polynomials, it's just a new polynomial. But when you actually divide them, what you're doing is you're changing it, and it's creating a different type of function. And really the main reason is due to the division. Division causes weird things to happen. And that's what I wanted to mainly focus on. So in these videos, we'll talk a lot about graphs and focus on asymptotes in terms like that. Let's just get started with the simplest rational function there is, which we often refer to as the reciprocal function. So let's let f of x be equal to 1 divided by x, which we refer to as the reciprocal function because of what it does. And what we want to do is find the asymptotes and the behavior towards the asymptotes. So we'll talk about what does that mean, and based on the context of the graph. But starting with the basic reciprocal function, we could always create a graph of a function by just plugging in values into the input and see what happens. And what's interesting to note about the reciprocal function, and the reason why we call it the reciprocal function, let's start by plugging in, say, 1, 2, or 3. And in your lecture notes, I've provided this graph to sort of look at these base cases. But if we were to plug in 1, we would have 1 over 1, and the output would just be 1. If we were to plug in 2, we'd have 1/2. 3, we'd get 1/3, and so on. And if we graph, those particular points, well, we would see that as you plug in a larger and a larger number into this function, what would happen is we're setting the denominator. And so we're going to get 1 divided by an increasingly large number. And when you divide by a larger and larger number, the value of it gets smaller and smaller. So as we can see, we go from 1 to 1/2 to 1/3, and so on, 1/4, 1/5, 1/6. And as this would progress, it's going to be an increasingly small fraction, because the larger the denominator, the closer and closer it will get to 0. And basically, this is what creates an asymptote in this particular function, is that as I continue to plug in larger and larger numbers, what happens is this does not get larger and larger. Like one of the key properties of a polynomial function, as we talked about a few weeks ago, is that when you plug in bigger and bigger numbers, polynomials get bigger and bigger, or smaller and smaller. They always trend towards infinity as x approaches infinity. But with a rational function, and we could write the end behavior of a rational function in the same way that we did with polynomials, we'd say that as x approaches infinity, the value of f of x actually does not approach infinity, it approaches 0 instead. Because, if I were to continue this trend and plug in, say, 10 into this, well, that would give me 1/10. Or if I were to plug in 100, that would give me 1 over 100. And the value is going to get increasingly small. But it's not going to go to minus infinity, it's going to get closer and closer to 0. And this is the exact idea behind what we refer to as the asymptote. And basically an asymptote, there's various different ways you can define asymptotes, and in calculus is defined using mathematical limits in this kind of idea. But an asymptote is either a vertical or horizontal line. Technically, you can have an asymptote which is a slanted line, or various different types of curvatures, but basically it's a line that describes the trending behavior of the function, and it kind of outlines what happens. It's something that you're going to get closer and closer and closer to it, but you're never actually going to intersect with it, and like over time it will get closer and closer to that position. Like in this particular case, the equation y is equal to 0 would be what we call the horizontal asymptote. So I'm going to go ahead and write the equation y is equal to 0 and refer to this. Usually we draw asymptotes using dotted lines, not solid lines. So I drew it as solid to start the outline, but it's a bit more proper to use a dotted line instead, because when we're making a mathematical graph, we always use a solid line to denote our function and the correlation between input and output, domain and range. but a dotted line is often used as like an outline, and that's kind of the idea of what an asymptote is. But in this case, yeah, it's the equation y is equal to 0, and we refer to this as a horizontal asymptote because it's just a horizontal line. And the reason that exists and that's there is like as I'm getting further and further to the right, what's happening is the graph is getting closer and closer and closer to that line. That's kind of the idea of the asymptote. But as it progresses further and further, it does not cross it. It will get infinitely close to it. And another thing you might wonder is, well, does it ever actually reach 0? But that's kind of the idea of an asymptote. It's something which outlines the direction which it heads, but it doesn't actually make it there. It's similar to how we said, well, as x with polynomials, as x approaches infinity, y approaches infinity. You can't actually make it to infinity. It's just kind of like the idea that this will continue to get larger forever. Whereas with a rational function, this will continue to get smaller forever, but it won't get infinitely small. It will get closer and closer to a particular value at 0. And notice that the equation of the asymptote is the same direction which we'd say the behavior heads towards. And if you're wondering, how do I know it's 0? Well, that's just because the smaller and basically the larger and larger value for x you plug in, like 10 would give you 1/10, would be 0.1, or 1/100th would be 0.01. There is no, you could make this as small as you want because the larger and larger number you plug in, the smaller it becomes. And there is no limit to how small that will become, but it will always be positive and it will be always greater than 0. So 0 is the limit of what this value trends towards. And anyways, that's, the asymptote is at 0, even though that function can't actually be 0. In the exact same way, notice that if we were to plug in negative values into f of x, like -1 or -2 or -3, again, we call it the reciprocal function because it just takes the input and it creates the reciprocal, which is just the word for flipping the fraction. So if I plug in -1, I would get -1. -2 would give me -1/2, and -3 would give me -1/3. And looking at the graph, -1 produces -1. -2 is -1/2, -1/3, and it's the same exact pattern. It's just opposite. And actually, the reciprocal function is an odd function, which we defined earlier when we were talking, earlier a few weeks ago. Notice the symmetry; it's symmetric across both y and x axis. And if you plug in a negative, what will happen is you just get the same numbers but negative. But anyways, that all being said, notice it's kind of the same pattern. Instead of getting closer and closer to 0 from above, it's getting closer and closer to 0 from below. And it would get closer and closer and closer to 0 as we go to the left. And again, how we'd write that is, well, as x approaches -infinity, which is just a way of saying, well, what's happening to the left? The value of f is also trending to 0 because it's getting closer and closer to that asymptote as we move. And anyways, as we said with polynomials, we refer to this as the end behavior, or the limit of that function as we approach infinity. And what's interesting about the reciprocal function is with basic numbers, we see what this sort of function 1 divided by x does. It flips over the input. But when we're analyzing the end behavior, we kind of see, well, what happens if you divide by an infinitely large number? It turns into basically 0. And actually, what's true is the exact same thing is true when you get closer and closer to 0. Because notice that as you head to infinity, it levels off and flattens out. Well, the same thing happens as you go towards 0, if we're looking at this part of the curve. So next thing I wanted to look at is what happens is as I plug fractions into this, like say, for example, 1/2 or 1/3. Well, again, if I were to do 1 divided by 1/2, dividing by a fraction is this, I could always compute by flip and multiply. Right, so if I had 1 divided by 1/2, that would flip and multiply, and that would change into 1 times 2/1. And notice that if I plug in a fraction, what I end up getting is a whole number. Or if I plug in 1/3, I would get 3, and so on. And if I graph those points, 1/2, 2, 1/3, 3, that trend would continue as well. So if I plug in smaller and smaller fractions, like say I was to plug in 1/4, that would give me 4. 1/5 would give me 5. And so on and so forth. Notice that as we plug in smaller and smaller values, what will happen is it will get larger and larger and larger. And what we refer to this as behavior towards the vertical asymptote. So basically in this curve, it has a horizontal asymptote, but it also has what we call a vertical asymptote and that's a vertical line. How you can kind of visually see an asymptote, because in rational functions they'll typically explode towards infinity in sort of a straight line, sort of look like a cliff, and that sort of looks like a cliff on both sides of the curve, and the asymptote always should fit right in between those cliffs. It can have more than one in certain cases, and we're going to look at more complex rational functions as we progress, but I wanted to start with a simpler one so we can kind of understand these terms and the nature of these. But we would refer to that, since it's a vertical line, it would have the equation x is equal to, and it would be 0 in this case because it's just going right through the origin. And we'd call this a vertical asymptote just because it's a vertical line. And in your homework, if it ever asks you to find the equation, make sure you're using x equals and y equals for your asymptotes, because asymptotes, we describe them using an equation, not, you don't want to just say 0, because that's not specific to, is it a horizontal line or is it a vertical line? And we could also describe the behavior towards the asymptote in a similar way. It's kind of like saying, well, as I'm getting closer and closer over here, it's getting really, really large. And the same thing happens on the negative side. If I plug in -1/2, it would flip to -2. -1/3 would flip to -3, and I would get these points here, right? And -1/4 would go down to -4. -1/10 would go down to -10. And the smaller and smaller fraction that I plug in would create a larger and larger number. So there's no limit on the process of this graph. And so what will happen is it will get closer and closer and closer and closer to this vertical asymptote without actually running into it or hitting it in exactly the same way as we go over here. And so how we write that is we say as x approaches 0 instead, because over here, notice that 0 is one thing that will not work in f of x, right? Because as we said before, you can't divide by 0. And if we're talking about the domain of this function, it would be all real numbers except for 0. And we looked at a couple examples of this earlier in the semester. And notice that it's not coincidental that the vertical asymptote occurs at the location to where the domain problem, and it creates a gap in the curve, or what we sometimes call a jump or a break. Because if I'm looking at the curvature of the rational function from left to right, it sort of is doing this cliff thing. It's kind of falling off a cliff, and all of a sudden it kind of pops up here and continues doing the reverse cliff. And remember, with one of the things I said about polynomials a few weeks ago is that they are smooth and continuous. Notice that these are rational functions are typically not continuous functions. They can be depending on the roots, and we're going to get into all that too. But notice there's a discontinuity because it's going down from left to right, and then it jumps and has a gap. It's not connected all the way through. Hence the discontinuity. But we could describe the behavior towards that asymptote or at the point of discontinuity, which is at x is equal to 0, the vertical asymptote, and say, well, what's happening as x approaches 0? But notice that it depends on whether what direction I'm heading from. Because if I'm going from left to right, notice that the function value is actually plunging to -infinity. But if I'm going from the right side to the left towards 0, it's actually jumping up to +infinity. And there's a way that we describe, how do we differentiate those two? Because as x approaches 0, it's not specific, because it's not approaching a specific thing. It depends on the direction. And basically how we write that is using this particular notation. So I'm just going to write it out, and then I'm going to kind of explain what it means in just a second. So on the right-hand side of the graph, notice that, if I'm coming from right to left, as I get closer and closer to that vertical asymptote, or one way that I've heard is if you think of the vertical asymptote as like a wall, you could think about what happens as you're getting closer and closer to the wall. And how we'd read this is as x approaches 0, basically notice I put a plus on in the location of an exponent. What that means is from the right. And again, this is just a mathematical notation. There's no mathematical meaning behind this. But if you ever see the little plus in the exponent, what all that means is as you're approaching the value of 0 from the right-hand side. Because it's different coming from the right-hand side than it is coming from the left. And as you can probably guess, when you put a little minus in the exponent, that means from the left-hand side. And in my experience, students can often, it's really easy to mix up the plus and the minus. But another way that you can remember why it's written this way is when we're on the right-hand side, we're coming from the positive direction, right? Because to the right is positive. And when we're coming from the left-hand side, we're coming from the negative direction. And that's kind of another reason why those symbols have been used. It's kind of a confusing way of writing it, but it's just a traditional notation in calculus. But basically, in this particular case, as we approach 0 from the right-hand side, it shoots up to positive infinity, which is how we'd write the behavior towards the asymptote from the right. And as we approach the asymptote from the left-hand side, which is what this means, f approaches minus infinity because it goes downward. And notice that notice the reciprocal nature here. When it goes to infinity, the function heads to 0. When we go to 0, the function heads to infinity. That's kind of the idea behind reciprocals in math. And this is a very key idea towards limits in calculus. And these are actually really important things to think about. You would never guess that this is important, because it seems so random and strange. But a lot of these ideas are quite important to infinite limits in calculus. And just to sort of read it, we refer to this as the behavior towards the asymptote. And also we refer to these as a right-handed limit versus a left-handed limit. And in general, a limit only exists if they're in agreement. Notice how here the limits do not agree. And so you would actually say the limit is undefined towards 0 in general. So if you were wondering as x approaches 0, what happens? But basically, this one would not, due to the inconsistency between the directions of the cliffs, basically, we would just say that you can't really describe the behavior because it's different depending on which direction you're looking at.